Bismillahirrahmanirrahim. Assalamu alaikum, dear student. Dr. M.Yousaf from the Department Chemistry Islamic College Peshawar is here. Gentlemen, today we will discuss Graham law of diffusion and effusion of gases. Graham law of diffusion and effusion of gases. In the last lecture, we have talked about diffusion and effusion. I would like to revise the definition of diffusion and effusion. By diffusion, we means the spontaneous mixing of gases due to random motion and collision until the mixture becomes uniform. That is, the spontaneous mixing of two or more than two gases due to random motion and collision until the mixture becomes uniform. That phenomena is called diffusion. While effusion is the leaking of a gas from a container through a small hole of molecular direction, one by one, without collision, and it always takes place from high pressure region to a low pressure region. So this is what we call as diffusion and effusion of gases. Now, regarding these two phenomena, Graham, he formulated a law which is called as Graham law of diffusion and effusion. So in this law, what we will discuss? We will discuss statement of the law, what the law says, and second is the proof of the law. 2 points we will discuss regarding Graham law. One is the statement of the law, and second is the proof of the law. Now, in order to give a statement, first let's say we have two gases, A and B. We have considered two gases, A and B. For simple reason, I have supposed that let the mass of the gas A is smaller than the mass of the gas B, as the sign below. We have considered two gases A and B. Let me suppose that the mass of gas A is Ma, the density of gas A is dA, and its rate of diffusion is Ra. That is, for gas A, we have supposed that its mass is Ma, its density is dA, its rate of diffusion is Ra, while for gas B, the mass is Mb, the density is dB, and the rate of diffusion is Rb. Now, this Graham law states that the rate of diffusion of a gas is inversely proportional. Look over here to this equation. Look over here. Graham law of diffusion and effusion states that the rate of diffusion of a gas, listen to me carefully, the rate of diffusion of a gas is inversely proportional to the mass, the square root of the mass of the gas. Once again, I may repeat. The rate of diffusion of a gas is inversely proportional to the square root of the molecular mass of that gas. But keep in mind, molecular mass and density, they are directly proportional. How? You know that density is equal to mass per unit volume. So instead of mass, you can write density as well. So the rate of diffusion of a gas, a single gas, I suppose, the rate of diffusion of a gas is inversely proportional to the square root of the molecular mass of that gas. That is, the rate of diffusion of a gas is inversely proportional to the square root of the molecular mass of that gas, or inversely proportional to the square root of the density of that gas. I have stated this law for a single gas, and that single gas is, let's say, A. But if we have two gases in comparison, like A and B, then this law can be stated that the relative rate of diffusion, here you see it is a ratio, between the rate of diffusion of gas A and the rate of diffusion of gas B. So another statement which can be given for this law, that the relative rate of diffusion of two gases, is inversely proportional to the square root of its molecular mass. That is, here Ra is inversely proportional to the square root of the mass of A, and the rate of diffusion of B is inversely proportional to the square root of mass of gas B. And similarly, the relative rate of diffusion of gases is also inversely proportional to the square root of their respective densities as shown here in this equation. But here, what we have to keep constant, we have to keep two things constant. One is temperature and the other is pressure. So in conclusion, we can say that the relative rate of diffusion of gases is inversely proportional to the square root of their molecular masses, or the square root of their inversely proportional to the square root of their densities, provided we keep temperature and pressure constant. And so this is the statement of Graham law of diffusion. Now, in order to explain and prove it, we have got two proofs: theoretical proof, and second is experimental proof. Here, theoretical proof and experimental proof. In order to prove it theoretically, here we say that it is rate of diffusion of gas A is inversely proportional to the molecular mass of the gas A. So, first proof we can give from what? The mass of the gases. And the second proof will be given from the density of the gases. So here we have divided the theoretical proof into two categories. One is proof from the molecular mass of the respective gases. And the second proof is from their densities. Because in the statement you see we have molecular mass or we have densities here. So the first proof is molecular mass. Now let's suppose we have gas A. We have gas A, ammonia here. Let gas A is ammonia here. As you see over here, I have denoted it by a small sphere. So I have taken this is ammonia. So gas A is ammonia. Let's say instead of A, it is ammonia. And instead of B, we have HCl. So Ra divided by Rb, it is the same equation. Instead of Mb, I will write MHCl. Look in this equation, I have written instead of Mb, MHCl. And instead of Ma, I have written MNH3. Just put the molar mass of HCl over here. The molar mass or molecular mass of HCl is 36.5 and that of ammonia is 70. So rate of diffusion of ammonia inversely proportional to its molecular mass. Rate of diffusion of HCl inversely proportional to the square root of its molecular mass. So just put here 36.5, put here 17, divide this by this and take the square root. You will get that the rate of diffusion of ammonia, ऊपर ammonia है और नीचे आपके पास है HCl. So HCl is 1. It means that if ammonia cover 1.5 meter, then HCl will cover 1 meter. It means ammonia is 1.5 times faster than HCl. And this is what Graham law of diffusion says, that lighter gases like ammonia will diffuse faster as compared to HCl, which is a heavier gas. So this is one proof by which we have proved Graham law that lighter gas ammonia diffuses faster than HCl. The second proof is from density. Now look over here, the same equation is again here RA divided by RB. Here instead of mass, here I take density of HCl. Here instead of mass of ammonia, I take density of ammonia. Now keep in mind the density of HCl is 1.66 and density of ammonia is 0.76. Divide this by this, take the square root, you will get again 1.5. So we have given two theoretical proof. One is the proof from mass, which says that ammonia is faster than HCl. How much? 1.5 times faster than HCl. And the second, we have proved it from the density of the two gases respectively. 1.66 is the density of HCl and 0.76 is the density of ammonia. Again, this proves that HCl is slower while ammonia is faster. These are two theoretical proof of Graham law. Now, experimentally, how in your simple laboratory you can prove it? That actually lighter gases diffuses at a higher rate and heavier gases diffuses at a slower rate. So for this purpose, you can take 100 centimeter long glass tube. So here, this is 100 centimeter long glass tube. The two end of this glass tube is open. This is also open and this is also open. Now what you will do, you will take a cotton swab. Of two cotton swab the maruchu shoda. Cotton ka piece. Take a cotton piece and soak it in HCl. Put the cotton piece here, and here take also a small piece of cotton and soak it in ammonia. Ammonia will diffuse from this end and HCl will diffuse from this end, and both of them they will combine here. And remember, when HCl and NH3 combine, you will get a white ring of ammonium chloride. Now, HCl is traveling from this end, ammonia is traveling from this end. The distance covered from this side up to this point is the distance covered by the ammonia, and the distance covered from this side is that by HCl. So in one experiment was found that if the total distance is 100 centimeter, then out of total 100, 60 centimeter is covered by ammonia from its side, and 40 centimeter is covered by what? by HCl from its side. So here the velocity of NH3 is directly proportional to the distance covered by NH3. Keep in mind. Remember, both the gases are diffusing simultaneously. That is, HCl is diffusing from this side, ammonia is diffusing from that side. So time is constant. Therefore, the rate of diffusion or velocity of NH3 is directly proportional to the distance covered by ammonia, and the velocity of HCl is directly proportional to the distance covered by HCl. Just put here the distance covered by ammonia is 60 centimeter, this one, and the distance covered by HCl is 40. Just divide this by this, again you will get 1.5. So here you have got two theoretical proof. One is this one from molecular masses, another from the densities, and third one is the experimental proof. All these three proofs, they suggest that ammonia, which is a lighter gas, it diffuses at a higher rate as compared to HCl, which is a heavier gas. Now look over here. What I have discussed is in your book. Sometime an MCQ can be asked. How? You will be given that ammonia is diffusing from this end. Sorry, HCl is diffusing from this end. Ammonia is diffusing from this end. तो वो आपसे पूछ सकते हैं कि एमोनियम क्लोराइड का जो वाइट रिंग बनेगा वो किस एंड को नजदीक होगा. तो NH4Cl इसका जो वाइट रिंग बनेगा वो HCl की एंड की तरफ जो है वो नजदीक होगा, क्योंकि ये स्लो डिफ्यूज कर रहा है तो ये कम फासला तय करेगा, ये इस एंड के करीब होगा और एमोनिया से दूर होगा. तो दो तरह के क्वेश्चन इस पे आ सकते हैं कि द वाइट रिंग ऑफ NH4Cl which is formed is near to what end. So it is near to HCl end and it is away from ammonia end. Okay, so another topic is proof of Graham law from kinetic molecular theory. Right now we have discussed Graham law of diffusion, and now we have to correlate Graham law with the postulates of kinetic molecular theory. We have to do what? We have to prove that Graham law and kinetic molecular theory, they are in agreement with each other. What Graham law says is also the points in kinetic molecular theory. You are familiar with kinetic molecular theory. One of the postulate of kinetic molecular theory is that at the same temperature, all gases have the same kinetic energy. This point should be kept in mind, that if we have same temperature and pressure, then all gases, they have the same kinetic energy. From this postulate, we will prove Graham law. Again, let's consider a gas A and gas B. And let's say that both the gases, they are taken at a constant temperature. That is, the temperature is constant for both gas A and gas B. The mass of gas A is ma, its velocity is va, and mass of gas B is mv, and its velocity is vb. Now, from the postulate of this kinetic molecular theory, we say that the kinetic energy of this gas must be equal to the kinetic energy of this gas B. So simply we can say that KEA must be equal to KEB. That is, kinetic energy of A must be equal to the kinetic energy of B. Now, KE A is equal to 1 over 2 MAVA square, and similarly KEB is equal to 1 over 2 MBVB square. This is cancelled with this one. You will get MAVA square is equal to MB square divided by VB square. Rearrange this equation, just rearrange. It's too simple. How it is rearranged? VB is shifted here, MA is shifted here. So you will get this equation. Now take the square root of this equation, VA divided by V. ये स्क्वायर रूट से बाहर आएंगे और ये स्क्वायर रूट के अंदर जाएंगे. तो VA divided by VB is inversely proportional to the molecular mass of A and molecular mass of B. Velocity of A is its rate of diffusion RA, and VB, velocity of B, is rate of diffusion of RB. Similarly, instead of mass, you can also write densities as well. So instead of mass, you can write density of B and density of A. Now here, a very simple MCQ is based on this Graham law of diffusion. Here, I have taken a simple MCQ. The MCQ is, which of the following gas diffuse at a higher rate? Yeah, a gas with high rate of diffusion. So the rate of diffusion of gas depends upon its molecular mass. So first you have to do what? You have to find out the molecular mass of all the gases and then select the correct choice. So here the molecular mass is 28. 12 is carbon and 16 is oxygen. It is also 28. It is also 28 and it is also 28. So remember, while solving MCQ, never pick the right choice. Remember, always eliminate the wrong one. You will be near to the correct choice one step. For example, if you look over here, it is 28, it is 28, it is 28. I have not included the third option, the fourth option. So the fourth option is all have the same rate of diffusion. Same rate of diffusion. So with this topic, we come to the end of chapter number 4. Remember, the rest of the topics in this chapter, they are omitted in the condensed syllabus. So this is the end of chapter number 4, that is gases. And inshallah, in next lecture, I will start chemical equilibrium. Chemical equilibrium, which is chapter number 7. Chapter number 7. The two other chapters, solid and liquids, they are covered by other teachers, and I will start inshallah chemical equilibrium, that is chapter number 7 for first year student. And keep in mind, even I will upload lectures during the winter vacation, which are going to be commenced from 24 December up to 11 January. So regularly, please subscribe the channel and go for more videos and more lecture in the winter vacation. Thank you very much.